There's a confusion that comes up remarkably often, and I think it's worth taking the time to address it carefully because it touches on something really fundamental about how science works and how we talk about what we know. You've probably heard people say that evolution is just a theory, as though calling it a theory somehow makes it less reliable, as though it's merely a guess or a hunch. And then you hear others respond by insisting, no, evolution is not a theory at all, it's a fact. Both of these positions, understandable as they are, miss something important about what scientists actually mean when they use the word theory. Let me start by untangling this confusion, because honestly, the word theory means very different things depending on whether you're chatting with friends or working in a laboratory, and this difference is at the heart of so much misunderstanding. In everyday conversation, when someone says, I have a theory about why the neighbor's dog keeps barking at 3 a.m, they usually mean they have a hunch, an educated guess, an idea they haven't really tested yet. It's tentative, uncertain, quite possibly wrong. We use the word casually, loosely. But in science, a theory is something entirely different, and this is where things get interesting. A scientific theory isn't a guess waiting to be promoted to a fact once we gather enough evidence. That's not how it works at all. A scientific theory is a comprehensive explanation of some aspect of nature that's supported by vast amounts of evidence from multiple independent sources, that has been tested repeatedly in different ways, and that makes predictions we can actually verify. It's not a lesser form of knowledge, it's actually a higher form, a framework that ties together countless observations and helps us understand them. So when scientists say that evolution is a theory, they're absolutely not expressing doubt or hedging their bets. They're placing it in the same category as the germ theory of disease, the atomic theory of matter, and the theory of gravity. These are our best, most thoroughly tested explanations for how things work. We don't go around saying that germs are just a theory or that atoms are just a theory, do we? We recognize these as robust, reliable frameworks that explain countless observations and allow us to make accurate predictions about the world. Now, here's where it gets really interesting, and I hope this clarifies rather than confuses. Evolution is both a theory and a fact, and there's absolutely no contradiction in saying this. Let me explain what I mean. The fact of evolution is simply this. Living things have changed over time. Species are not fixed and unchanging, frozen in the forms we see today. They have ancestors that were different from them. If you go back far enough in time, you and I share ancestors, not just with chimpanzees, which most people know about, but with oak trees and butterflies and even bacteria. I know that sounds strange, maybe even uncomfortable, but it's an observed reality, documented in multiple independent lines of evidence that all point to the same conclusion. We can see this change in the fossil record, where we find organisms that no longer exist and can trace lineages changing over millions of years. We can see it in the geographical distribution of species, where islands have unique creatures that are clearly related to but distinct from mainland forms. We can see it in the nested hierarchies of DNA sequences, where more closely related organisms share more genetic material. We can even observe it happening in real time, right now, in laboratories and in nature, as bacteria evolve resistance to antibiotics, or as populations adapt to changing environments over just a few generations. This isn't speculation, this is observation. The theory of evolution, by contrast, is our explanation for how this change happens. It's the framework that tells us the mechanisms driving the process, the why and the how. Natural selection is the centerpiece of this theory, the elegant idea that organisms with traits better suited to their environment tend to survive and reproduce more successfully, passing those advantageous traits to their offspring. Over many generations, this process shapes populations, leading to adaptation and eventually to the formation of new species. This explanation, first articulated clearly by Darwin and Wallace back in the 19th century, and refined and expanded enormously since then with genetics and molecular biology, is supported by evidence from paleontology, comparative anatomy, embryology, biogeography, and most powerfully in recent decades from our ability to read and compare DNA sequences. Let me try an analogy that might help make this distinction clearer. Gravity is a fact. Things fall. If you drop your phone, it falls to the ground. We can observe this, measure it, predict it with precision. Nobody seriously doubts that objects attract each other. But the theory of gravity, whether Newton's formulation or Einstein's more refined general relativity, is our explanation for why and how gravity works, the mathematical framework that describes gravitational attraction and allows us to calculate planetary orbits and predict how light bends near massive objects. The fact doesn't depend on having a perfect theory. Even if our theory of gravity were somehow completely wrong, which it isn't, things would still fall. Similarly, evolution, the change in living things over time, is a fact regardless of whether our theoretical understanding of all the mechanisms is complete or perfect. But I want to emphasize, our theoretical understanding is remarkably good. Evolution by natural selection is supported by evidence of a kind and quantity that scientists in other fields might genuinely envy. Let me walk through some of this evidence, not exhaustively because that would take days, but enough to give you a real sense of just how thoroughly supported this theory is. Start with the fossil record. Now, I should be honest, fossils are by their nature incomplete. Most organisms that have ever lived left no fossils. Fossilization requires very specific conditions, the right environment, the right chemistry, rapid burial, and the chances of any particular organism being preserved are vanishingly small. Most living things just decay and disappear. Yet despite these limitations, we have hundreds of millions of fossils representing hundreds of thousands of species. And what we see in these fossils is a remarkably clear pattern. In the oldest rocks, dating back billions of years, we find only simple, single-celled organisms. As we move up through the geological layers, through younger and younger rocks, we see the appearance of more complex forms. First, simple multicellular organisms, then the great explosion of animal diversity in the Cambrian period about 500 million years ago, then fish, then amphibians crawling onto land, then reptiles, then mammals and birds. We never find rabbits in Precambrian rocks that are billions of years old. We never find modern birds alongside dinosaurs. The sequence is consistent across the globe in rocks from every continent, and it's exactly what we'd expect if species have been branching off from common ancestors over vast stretches of time. Even more striking, and I find this genuinely exciting, are the transitional forms, fossils that show intermediate characteristics between major groups. We have Tiktaalik, a remarkable fossil from about 375 million years ago, a fish with features pointing toward land-dwelling vertebrates with a neck with wrist-like joints in its fins, showing us how our very distant ancestors made the transition from water to land. We have Archaeopteryx, with feathers and wings like a bird, but teeth and a bony tail like a reptile, illuminating the origin of birds from dinosaurian ancestors. We have a beautiful series of fossils documenting the evolution of whales from land-dwelling mammal S, showing the gradual shift from legs to flippers, the migration of nostrils to the top of the head to form a blowhole, the development of tail flukes. These aren't just random lucky finds. Scientists can predict what kinds of transitional forms should exist, in what geological layers we're likely to find them based on the theory, and then teams go out and actually find them. That's the power of a good scientific theory. But fossils are just one line of evidence, and honestly, even if we had no fossils at all, evolution would still be overwhelmingly supported. Consider comparative anatomy, something you can see for yourself if you look. When you examine the forelimbs of different mammals, you see the same basic bone structure, modified for wildly different purposes. A human arm, a bat's wing, a whale's flipper, a horse's leg, all built on the same underlying skeletal framework, the same arrangement of bones, just stretched or compressed or modified in various ways. Why would that be? Why would a designer use the same basic structure for such radically different functions when starting fresh might yield better designs? But it makes perfect sense if these structures are all inherited from a common ancestor and have been modified by natural selection for different uses over millions of years. Then there's embryology, the study of how organisms develop. This is fascinating stuff. Embryos of very different species often look remarkably similar in their early stages. Human embryos, for instance, have structures that look like gill slits and have tails. features we share briefly with fish and reptile embryos before developing along our own path. Why would a human embryo develop these structures only to lose them later if we're not related to organisms that retain them as adults? It's exactly what we'd expect if we share common ancestors with fish, and if evolution works by modifying existing developmental pathways rather than designing everything from scratch each time. The evidence from biogeography, the study of where species live, is equally compelling. The distribution of species across the planet makes sense in light of evolution and continental drift, but it would be quite puzzling otherwise. Australia has marsupials, pouched mammals, filling ecological niches that placental mammals fill elsewhere. Why? Because Australia separated from other land masses early in mammalian evolution, and marsupials evolved in isolation there. Islands have unique species that are closely related to but distinct from the nearest mainland species because populations become isolated and evolve independently. The Galapagos finches that helped inspire Darwin show this beautifully. Different species on different islands, all clearly related to South American finches, but adapted to local conditions, different beak shapes for different food sources. And then we have molecular biology and genetics, evidence that simply wasn't available to Darwin, but that has confirmed and extended his theory in ways he could never have imagined. DNA is like a historical document written in a chemical code, and we can now read that code. When we compare the DNA sequences of different species, we find the same nested hierarchy of similarities that we see in anatomy. Humans and chimpanzees share about 98 to 99% of their DNA sequences. We share less with monkeys, still less with mice, even less with fish, and very little with bacteria. This pattern of genetic similarity precisely matches the pattern of relatedness we'd infer from anatomy and fossils. If we'd gotten different patterns from DNA than from fossils, that would have been a serious problem for evolutionary theory. But we don't. Everything fits together. We can even find broken genes, pseudogenes, that no longer function, shared between related species in the same broken state, like typos copied from one manuscript to another. These make sense only as shared inheritance from common ancestors. Why would separate creations share the same genetic mistakes? We can trace specific genetic changes and sometimes even correlate them with specific environmental pressures. We can watch evolution happening in real time. Bacteria evolving resistance to antibiotics aren't just adapting in some vague sense. We can identify the specific mutations that confer resistance. Watch them spread through populations within days or weeks. See natural selection in action at the molecular level. We've observed new species forming in laboratories and in the wild. We've documented populations diverging, adapting to different environments, accumulating differences that eventually make interbreeding impossible. This isn't ancient history. This is happening now. The theory of evolution makes predictions, specific testable predictions, and when we test those predictions, they hold up remarkably well. We can predict that organisms sharing a recent common ancestor will share more genetic sequences. We can predict where we're likely to find certain types of transitional fossils in the geological Rico R&D. We can predict how quickly organisms with short generation times should evolve compared to those with long generation times. These predictions are testable, and they've been tested thousands of times in thousands of different ways by thousands of different scientists. And the theory continues to hold up. When a theory keeps making successful predictions, that's when scientists start to take it very seriously indeed. Now, does this mean we understand absolutely everything about evolution? Of course not. That would be absurd. There are ongoing debates among evolutionary biologists about the relative importance of different mechanisms, about the tempo and mode of evolution, about the role of random genetic drift versus natural selection in particular cases, about how developmental processes constrain or channel evolutionary change. These are normal, healthy scientific discussions, the kind of refinement and extension of theory that happens in any active scientific field. They don't undermine the basic framework any more than debates about the details of quantum mechanics undermine atomic theory. Scientists arguing about details is a sign of a vigorous living field of research, not a weakness. It's also worth being clear about what evolution doesn't claim to explain, because there's often confusion about this. Evolution is a theory about how life changes over time once it exists. It's not a theory about how life originated in the first place, how non-living chemistry first gave rise to living organisms. That's a separate question, one we're making real progress on but haven't fully answered. There are some promising ideas and fascinating experiments, but it's not settled science yet. Evolution also doesn't explain the Big Bang or the origin of the universe. It doesn't make claims about the ultimate meaning of life or whether there's a purpose to existence. It's a scientific theory about a specific natural process, and it's spectacularly successful within that specific domain. I know that some people resist accepting evolution because they feel it conflicts with their religious beliefs, and I want to tread carefully here because I know this is sensitive territory for many. Evolution is a scientific theory based on evidence, and it stands or falls on that evidence regardless of anyone's religious convictions or lack thereof. But I think it's worth noting that many religious people, including many scientists who are themselves deeply religious, have found ways to reconcile their faith with evolutionary theory. They see evolution as the mechanism through which their deity chose to create the diversity of life, as the process rather than contradicting creation. Whether you find that persuasive is entirely a personal matter, but the point is that accepting the scientific evidence for evolution doesn't necessarily require giving up every form of religious belief. What evolution does contradict, and I should be honest about this, is a literal interpretation of creation stories that claim life appeared in its present form relatively recently, that species are fixed and unchanging, that humans have no evolutionary relationship to other animals. These specific claims are contradicted by overwhelming evidence. Accepting evolution requires accepting that these particular stories, whatever their spiritual or metaphorical value, are not accurate descriptions of natural history. That can be difficult for people, and I understand that. It sometimes means rethinking beliefs held since childhood, beliefs tied to identity and community. That's not easy. Let me return to the question of why evolution is called a theory, because I think this is really important. It's because in science, theories are not inferior to facts. They're different kinds of things, and both are valuable. Facts are observations, things we can see and measure. Theories are explanatory frameworks that account for many facts and allow us to understand them in a coherent way, to see the patterns and connections. Saying evolution is a theory is not a limitation or qualification or hedge. It's a recognition of what kind of knowledge we're dealing with. It's our best explanation for the diversity and relatedness of life on Earth, supported by converging lines of evidence from multiple scientific disciplines tested repeatedly in different ways, productive of new insights and discoveries. Could it be wrong? In principle, yes. Science doesn't deal in absolute certainty, and any scientist who claims otherwise is misleading you. But it would take extraordinary evidence to overturn evolution at this point, evidence that would also have to explain why all the current evidence appears to support it so strongly. It's a bit like asking whether atomic theory could be wrong. Could we discover tomorrow that matter isn't made of atoms after all? In some abstract philosophical sense, yes, but it would require not just new evidence, but an explanation for why atomic theory has been so successful for so long, why it makes such accurate predictions, why all our observati ons seem to confirm it. The same is true of evolution. We'd need not just evidence against it, but an alternative explanation for all the evidence that currently supports it. What distinguishes science from other ways of knowing is this willingness to follow evidence wherever it leads, to update our understanding when new information comes in, to hold our conclusions provisionally, rather than as absolute certainties that can never be questioned. But provisional doesn't mean wishy-washy or uncertain in the casual sense. We're provisionally confident that the Earth orbits the Sun, that DNA carries genetic information, that species evolve. These conclusions are as solid as scientific knowledge gets, as reliable as anything we know about the natural world, even though we remain, in principle, open to being proven wrong. When people say evolution is just a theory, they're often trying to place it on equal footing with other ideas like intelligent design or special creation, as though all explanations deserve equal consideration and we should let people decide for themselves. But this misunderstands how science works. Not all explanations are equally good. Some are supported by evidence and make testable predictions. Others aren't and don't. Evolution is supported by massive amounts of evidence from multiple independent sources. It makes predictions that have been confirmed again and again. It's unified biology, making sense of observations across paleontology, genetics, anatomy, ecology, behavior, and more. The alternatives typically either make no testable predictions at all or make predictions that have been tested and falsified. Understanding evolution isn't just about winning arguments or having the right opinions about science, though. It's about understanding our place in nature, our relationship to other living things, the deep history written in our own DNA and in the DNA of every organism around us. It illuminates why organisms are the way they are, why some bacteria make us sick and how they develop resistance to drugs, why crops and livestock respond to selective breeding, why invasive species can wreak havoc in new environments, why conservation efforts need to account for genetic diversity. It's practical knowledge with real applications in medicine, agriculture, conservation, not just abstract theory. There's something genuinely profound and humbling about understanding evolution, about recognizing that we're part of this great tree of life, that we share ancestors with every living thing, that the same processes that shaped the wings of butterflies and the eyes of octopuses shaped our own minds and bodies. It doesn't diminish us. If anything, I think it enlarges our sense of connection to the natural world. We're not separate from nature, standing outside it, looking in. We're part of it, deeply embedded in it, products of the same ancient processes that have generated all the beauty and diversity around us. So is evolution a theory? Yes, absolutely, in the scientific sense, and that's a mark of its strength, not its weakness. Is it a fact? Yes, in the sense that life has changed over time and species are related by common ancestry. These aren't contradictory statements. They're different aspects of the same reality viewed from different angles. The fact is what happened. The theory is our best explanation for how and why it happened. Both are supported by evidence of extraordinary breadth and depth, accumulated over more than a century and a half by thousands of scientists in many countries working in many different fields, all arriving at the same basic conclusions. Understanding this distinction between theory as scientific explanation and theory as casual guess is part of what it means to think scientifically, to appreciate how science builds reliable knowledge about the natural world. It's a small step, perhaps, but an important one in developing the kind of critical thinking and evidence-based reasoning that serves us well not just in understanding evolution, but in navigating a world full of competing claims and complex information. We don't have to take anyone's word for it. The evidence is there, accumulated in museums and journals and databases, waiting to be examined by anyone willing to look at it carefully and honestly and follow where it leads.